Hello, chemists, and welcome back. Before we get into today, I want to make sure that you've all seen the lesson from yesterday as well as read through the notes in the booklet, because those will be helpful to look at before you get to this video. This video is going to be an explanation of the answers to the notes in the booklet that you got, so the questions in the booklet that you got yesterday. So I'm just going to briefly go through as little reference and explanation. This key will also be posted, so if you prefer to just read through it and have it open, you can do that as well. But without further ado, let's take a look at some of these things that got asked yesterday. Then I'll also mention, before we get going too much, I'm going to post another practice sheet and a key today that you can do if you'd like extra practice on the whole temperature phase diagrams, which could be helpful for you as well. So yeah, here we go. Questions for phase change notes. Explain the relationship between heat and kinetic energy. So remember, heat is a measure of the average kinetic energy. They're sort of one and the same. So as heat increases, so does kinetic energy, but that's because heat is a measure of kinetic energy. So you can think of kinetic energy as in like the movement of particles and how fast they're moving, how much they're moving, being directly related to temperature and heat, because they're all like measuring the same sort of molecular movement. Classify each phase change as endothermic or exo. Melting is endothermic because you have to put heat in. In general, I'll preface this with saying if you're going towards gas, then you have to put heat in. If you're going towards solid, you have to take heat out. So melting, it's going closer to gas, it's going from solid to liquid, so you need to put energy in, so it's endothermic. Freezing, on the other hand, is going in the opposite direction, towards solid. It's going from liquid to solid, so that is exothermic. Evaporation, it's going from liquid to gas, so that's moving up in energy, so it takes in heat. Condensation is moving down in energy from gas to liquid, so it gives off heat. It's exothermic. Sublimation, it's solid to gas again, so it's moving in like an increase in energy, so it needs to take energy in. Whereas deposition goes from a higher energy state, gas, to solid, so that gives off energy. It's exothermic. All right. Summarize how melting occurs. Energy is added to overcome the intermolecular forces and lessen density from solid to liquid. So we're saying here that you're going to add energy into a substance, and that energy is going to make the molecules become more energetic and break apart from the intermolecular forces, if you remember that analogy of like a magnet snapping apart. And that'll lessen the density from, which will go from solid to liquid. Freezing, on the other hand, energy is released to strengthen the intermolecular forces, or sort of snap that magnet back together, and it increases the density from liquid to solid. So these are just opposites here. One is adding energy to overcome the forces of attraction, and one is releasing energy to give in to the forces of attraction. Alright, 5a. You have a block of ice with a temperature of negative 10 degrees Celsius. You record the temperature change as you heat it to a liquid with a temperature of 20 degrees Celsius. You notice the temperature doesn't change when the ice is changing from solid to liquid. Explain why. These are those plateaus in the graph that we were talking about yesterday, and we're going to look at again today later on. But basically, when you're during a phase change, energy added, I'll just kind of show you what I mean here as I scroll down. We're talking about these flat parts on a graph right here. But the energy added overcomes the intermolecular forces during phase changes, but does not increase temp. All the energy that's going in is just working on loosening the intermolecular forces here. So although you don't see a change in temperature, it's still doing lots of work. If you are melting pure water from solid to liquid, what temperature would you expect this to happen at? 0 degrees Celsius, because that's the melting point of water. And if you are freezing it in the opposite direction, what temperature? Also 0. The melting point and freezing point are the same for any substance, and then the boiling point and the condensation point are also the same. We use water because they're easy to remember. It's 0 degrees Celsius and 100 degrees Celsius, but every substance will have a unique set of characters there. Summarize how evaporation occurs. So energy is added to free liquid particles from IMF and change into gas. So by free liquid particles, we mean we're going to break free from the intermolecular forces of attraction. And we do that by adding energy to allow the liquid molecules to sort of escape and stop being attracted to one another. So then they can just become gases and start moving in any direction and like being being more energetic. So we're breaking free from like the liquid attraction that keeps the liquid together and moving it into a gas by adding energy. Why can liquid evaporate without the addition of any heat? In other words, why can't it occur in a glass of water sitting at room temperature? So in a liquid, surface molecules can escape and overcome vapor pressure at a slow rate. If you want more clarification on this, I suggest you go to the video from yesterday because I had some images up of how that works. But basically, surface molecules can sometimes escape and become a gas even when like the entire liquid isn't boiling. Using KMT and your knowledge of evaporation, why does sweating make your skin feel cooler? This one's interesting, but when sweat evaporates off your skin, it has to take some heat in, because evaporation is endothermic, and just taking that heat in from around your skin can actually cool you down slightly. For each of the following methods, predict why, why would this speed up the rate of the evaporation on a molecular level? So heating increases the energy in particle movement, and the faster and more energetic particles have become, the easier they can escape from intermolecular forces and change state. So that's helpful. Surface area similarly, if there's more area, that means there's more molecules on the surface, and the more there are, just statistically speaking, you're going to be more likely to have evaporation happen, and that can speed it up as well. You're just giving it more opportunities. Adding an air current's an interesting one. What that would do is sweep away the air above and lower the pressure above, and with lower pressure above, it takes less force to escape and evaporate. Summarize how condensation occurs. Energy is lost from a gas, allowing intermolecular forces to snap back into place and eventually become a liquid. This is like just the opposite, not the opposite, but a very parallel one to freezing. It's just instead of going from liquid to solid, we're going here from gas to liquid. So we're going from like no IMFs to slight IMFs. Using your knowledge of KMT and condensation, explain why droplets of water form on a cold can of Pepsi that is left to sit on a table on a hot day. So when the warm air from like the summertime is able to touch the cold surface of the can, let's say it's been in a cooler with some ice in it and stuff, that can cause condensation because like the cold can will cause the energy and the temperature of like the warm air to decrease rapidly, and that loss of energy can compel a condensation. What is the vapor-liquid equilibrium? That's when the pressure of the gas above a liquid is equal with the vapor pressure inside the liquid. When we look at like boiling or something, and it's just bouncing out, so nothing's coming in and nothing's going out. Again, with that, look at the image in your notes, and look at the image in the presentation from yesterday to get an idea of how that maps out. Explain why water boils at a lower temperature in Denver in the mountains than in Death Valley, like way in the desert below sea level. So, there's lower atmospheric pressure at high altitudes. That's why when you climb like Mount Everest or something, you need to take oxygen. But yeah, when there's less pressure, there's less pressure required to be overcome to start boiling, so you don't need to get the molecules moving as quickly or as energetically to boil when there's less vapor pressure in the surroundings. Draw a diagram to represent sublimation and deposition. So here you can really just draw anything that's showing a solid to gas, anything that makes sense to you. I just took a simple one here where you're going solid to gas with like the little arrows drawn, but you can be as creative or non-creative as you feel like there, as long as you get the whole map of it. Okay, so now these are important types of questions. You're going to see stuff like this a lot in this unit in chemistry, and moving forward, where you're going to see like a freezing and boiling point graph. And here it's really helpful to just be able to understand what each of these segments represents as far as the chemical goes. So again, the flat points are state changes, and then like the parts that are moving up or down are when something's a solid, liquid, or gas. So freezing point is B. That's when it goes from a solid at its lowest energy state to a liquid. The boiling point is D. That's when it's going from a liquid to a gas. I'll zoom out here so you can see more. There we go. So you can take a look and scan down here, but let's just like before really going through here, let's say what's happening. So here at A we have a solid. The solid is going to get heated up and energy is added until it gets to the melting point. Then at this melting point, all the energy added is going to overcome the intermolecular forces and loosen them until they're all the way loose in all the molecules. Then it can keep warming as a liquid, and it's going to keep warming as a liquid until it reaches the boiling point. Then all the energy is going to get rid of those intermolecular forces entirely and free the molecules to become gas. Then, once it's all become gas, then it's able to start gaining heat as a gas, and that's the state here. So we have solid, melting, liquid, evaporation, and gas. So then all these kind of fall in line. Like here, A is where the solid is being warmed, C is where like the liquid is being warmed. So you can just pause here if you want all the letters. One thing I do want to talk about though is a letter that shows a change of potential energy. That's these phase changes, because the potential is changing because the intermolecular forces are changing, but the actual kinetic energy isn't changing unless you see a change in temperature. So phase changes change the potential energy, and like the heating and cooling of different substances change the kinetic energy. Over here, this is a bit of a more confusing diagram to look at initially, but all this is saying is that the amount of pressure and temperature correlated for when a gas would boil. This is kind of a preview for next week, or not next week, sorry, next lesson too, when we start to talk more about gases. But just remember here, a torr is the same as a millimeter of mercury, an mmHg. But this, if you had trouble with this already, don't fret it too much, because we're going to be looking at stuff like this more next week. Not next week, I keep saying that, next lesson. But so here we're just like following the graph to get these readings. At what temperature would liquid A boil at an atmospheric pressure of 400 torr? So we have to find A, and we find an atmospheric pressure of 400 torr. We follow it along, and imagine you're drawing a line down. This is sort of like what you were doing in like grade 10 motion or something, or physics. And we get that. I was just being approximate with these because you have to kind of eyeball them. So if you were in the same ballpark, you got it right. I'm not like going to be too precise here. I just want to make sure the idea is coming across right now. So we go to 40 or 400, then we come down and we end up like maybe even at 38. I just wrote 40 because I was being generous. Like if we go to right there, it's about right. Then liquid B, same. We're going to follow this all the way across to liquid B. Here we are. We're going to go down and we're at about 70. Liquid C, at 400, we'd need about 100 degrees to boil it. So this is just saying temperature again on this axis, vapor pressure here. It's showing what temperature you need to heat a substance to boil it, depending on the pressure, because the lower the pressure, the easier it is to boil something. Then this is just in the opposite direction, so what's the atmospheric pressure to boil at 35? You just have to find 35, then go up. So here's for C, it would be 50, just like we have here. If you keep going up for B, it would be 150, and, I put 200, let's see that. I guess it's almost at 200. We can call that 200. But so that's just reading the graph. And then the normal boiling point, this one's a bit tough if you don't know what it's actually asking for. 760 torr is considered standard, so that's what it means by normal. But here we're at 760, and we just have to do the same reading as well. These are a bit tricky. Again, don't fret too much on this, since we'll look at stuff like this as we move forward. But if you already can kind of see how this is coming together, then you're in great shape. And again, what liquid has the strongest intermolecular forces? Whatever takes the most energy to boil. That has the strongest hold together, so in this case it would be C, because it's requiring the most temperature. Anyways, chemists, we're going to keep practicing stuff like this and looking at gases as the week goes on. Please email me with any questions you may have, mrbsciencemb@gmail.com, and have a lovely day.